the last step here, what will I have? Well, the very last step is you go to the n minus 1th place derivative, and then you postulate there's a point in between where the nth derivative at some point c, I guess this is the one that's Cn, right? This is the one you want to call C, is 0. There exists a C n such that this creature is 0. Okay. And now, is that what I wanted to show? Is that what I wanted to show? Yeah, this is what I wanted to show. Okay, so, oh, nice, nice. What is the upshot? Why does that show that f is p plus this creature? What's that? Yes. So I can plug this back into Cyclops Smiley, and now Cyclops Smiley is true. Here you can view B as the point I'm interested in, right? So B here is playing the role of this x. Okay. You want to know what f of B is in relation to Pn minus 1 of B, then that's where Cyclops Smiley finishes the argument. Okay, so if this were 0, then we solve for m. That's right. And if we solve for m, then f of b will hold for that m. So let me just make sure I get this in here. So this shows m is, in fact, Fn of c over n factorial. Then in Smiley, we get the result. Okay. Okay, this is actually, I like this proof a little better than the one that's in Rudin. Yeah, I like this one better. Of course, we're using the mean value theorem several times here, yes? Basically bootstrapping down these derivatives through a clever choice of function. Now, of course, you're seeing very, very, very slick arguments here, and I should just warn you that you're seeing basically the product of many, many decades of people thinking of better and better proofs. Okay, the original proof of Taylor's theorem of mean value theorem due to Cauchy, 1823, is actually wrong. Okay, there's some issues with the proof, and it wasn't really gotten right until I think it was Bonnet in the 1860s actually had the first valid proof of the mean value theorem. Question?
I don't know. The way the theorem is stated, it seems like the c is fixed for all x, but doesn't the c change for each x?
Let's see. So your question here is c could depend on x. C actually here depends on, C could depend on the point x. Let's see here. Sorry, did I write this correctly? So we have a function we want to establish. Yeah, so I should, right, so c could depend on x. Maybe I should make that clear here for some c. and this may depend on x. Actually, in fact, what we've shown is that this c lives in between a and x. Maybe this last point b could even, this last point b could even be changed to x, if that helps. Let's see, do I buy that? Is that what I want to say? X is over and c is in between? Yeah. Could even depend on. Now this clearly depends on, could clearly depend on x. It certainly lives between a and b. Yeah. But the c could change. Yeah? Does that address your issue? You were trying to correspond the two, right? Yeah. Okay, excellent. So that's the content of Taylor's theorem, and you'll note a few examples in the homework where you're going to use basically all the homework problems involve the mean value theorem or Taylor's theorem applied in some way, some clever way, usually. All right. Okay, great. So let's take a couple-minute break, and after the break, I want to talk about sequences of functions, which is